Hello everyone. Let's analyze. So we've discussed what it means for sequences to converge. Now of course we know that a sequence is a function from the natural numbers to the reals. But what about functions that are not from the natural numbers? Functions from the real line or subsets of the real line? How can we define what the limit of such a function is? Well, the idea is similar, but we swap a natural number big N for a real delta. Now first, let's consider the case that f is a function from the entire real line to a real codomain. So let f map real numbers to real numbers. Then f has a limit L at x naught if and only if for every epsilon greater than 0 there exists a delta in R for which the following is true. If the difference of x and x naught in absolute value is less than delta, but greater than 0, in other words, x and x naught are not equal, then the absolute value of the difference of f of x and L is less than epsilon. So a couple of things to notice about this definition. One is x and x naught are not equal because their difference is greater than 0. And when we read there exists a delta, we should probably think in our mind there exists a corresponding delta to epsilon. In other words, for every epsilon greater than 0, there is a corresponding delta. That is, a delta that corresponds to epsilon. Meaning if someone gives you a different epsilon, you're likely to need a different delta. And of course you choose delta so that if this statement is true, then this statement is true. So imagine someone does give you an epsilon greater than 0 and challenges you to find a corresponding delta greater than 0 that would guarantee that f is within epsilon of L whenever x is within delta of x naught, but not equal to x naught. If you can meet their challenge, no matter what positive epsilon is thrown at you, then you've proven that the limit as x approaches x naught of f of x is L, to use standard notation. And of course such a challenge ought to be seen as a personal affront and met with the righteous fury of an analyst in their quest to find the right delta to parry the epsilon offered. But, well, what of functions that do not have the whole real line as its codomain? How can we generalize this definition to any arbitrary domain? Well, if we were to speak of domain elements x arbitrarily close to x naught and not make fools of ourselves, we must be assured that there are elements of the domain as close to x naught as we like. Therefore, the number x naught must be an accumulation point of D, though not necessarily contained in D. So this definition of a limit is more general, and it's the one we'll use from here on out. Let f map a domain D to R, where the domain E is a real domain and has x naught as an accumulation point. Then f has a limit L at x naught if and only if for every positive epsilon there is a real delta for which the following statement is true. If x is in the domain and x minus x naught an absolute value is less than delta but not 0, then the absolute value of the difference of f of x and L is less than epsilon. As I said, this definition is more general. This will be the one that we'll use. But of course, if your domain is the entire real line, then this definition simplifies just slightly to the first definition, since of course every real number is an accumulation point of the real line. So let's take a look at some examples. So consider a domain of every real number but 1. Let the function f be defined as f of x equals x squared minus 1 divided by x minus 1. Of course, the function is not defined at 1 because to evaluate the function at 1 would require you to divide it by 0, which of course you can't do. However, 1 is an accumulation point at this domain. Now prove that the limit of f at x not equals 1 is 2. Well, let epsilon be arbitrary. We'll start where we always start. Epsilon's an arbitrary positive number. And let's choose a corresponding delta. In this case, we'll choose delta equals epsilon. And you'll see shortly why we chose that. So if x minus 1 in absolute value is less than delta, which is epsilon, but greater than 0, then f of x minus 2 in absolute value is equal to, well, f of x is x squared minus 1 divided by x minus 1. And that's a perfectly valid operation to take because remember, x here is in the domain, meaning it's not 1. And if x is not 1, x squared minus 1 over x minus 1 is equal to x plus 1 times x minus 1 divided by x minus 1. Of course, those x minus 1 factors cancel, and f of x becomes just x plus 1. In fact, f of x is equal to x plus 1 for every x not equal to 1, which is, of course, every x in the domain. And x plus 1 minus 2 is equal to x minus 1, right? So, my function evaluation minus the proposed limit equals x minus 1. X minus 1 is less than delta, and delta is equal to epsilon. So if x minus 1 is less than delta, then f of x minus 2 is less than epsilon. All right, let's consider another example. Let D be the entire real line. And let f be defined as f of x equals x squared. Prove that the limit as x approaches 2 of f of x equals 4. Now, I'll start my proof as I always do. For these limits, let epsilon be greater than 0 and arbitrary. And let's choose delta to be whichever of those two numbers is smaller, 3 or epsilon divided by 7. Of course, if someone gives you a very small epsilon, epsilon divided by 7 is likely to be less than 3. But if someone gives you an epsilon greater than 21, then choose delta to be 3. Now, if the absolute value of the difference of x minus 2 is less than delta, right? Remember, we want to show an if-then statement, right? If x minus 2 is less than delta in absolute value but not 0, then my function evaluation minus my proposed limit, which is x squared minus 4, is equal to the absolute value of x plus 2 times x minus 2. Well, I know what this is less than, but what about this? Well, let's write that in terms of x minus 2. X plus 2 is x minus 2 plus 4. I can distribute my absolute value to the two products. It's equal to the absolute value of x minus 2 plus 4 times x minus 2. Using the triangle equality applied to this term, that's less than the absolute value of x minus 2 plus 4 times the absolute value of x minus 2. Now, this term I know is less than epsilon over 7 by my choice of delta, and the fact that I'm assuming this is true. I also know that x minus 2 in absolute value is less than 3, again by my choice of delta. So then this is less than or equal to 3 plus 4 times epsilon over 7. Since 3 plus 4 equals 7, trust me, I'm an expert, this is equal to epsilon. Therefore, x squared minus 4 is less than epsilon. In fact, actually, this here should be a strict less than or equal to, as a typo. And we've shown that, in fact, f satisfies the definition of a limit at x not equals 2, and that limit is 4. But, wait a second. Where do I get such beautiful deltas? I mean, what kind of crystal ball predicted that if I chose, based on epsilon, delta to be the smaller of 3 or epsilon over 7, right? If I chose delta to be that would be exactly what I needed to satisfy my epsilon condition. How did I pick such a delta? Well, let's take a peek behind the curtain of the delta factory, and let's look at how to break down such a problem. Now remember, I can only control the bound delta to the difference x minus 2 is less than delta in response to an arbitrary epsilon. And using my control of delta, what do I need to guarantee? I need to guarantee that the absolute value of x squared minus 4 is less than epsilon. That's what I need to guarantee. Now I know that the absolute value of x squared minus 4 equals the absolute value of x plus 2 times the absolute value of x minus 2. So I know that. And I see that, well, this is the term that I have control over the bound. Right? I get to choose what that's bounded by in order to guarantee this result. So a plan emerges. I'm going to choose delta that guarantees both this is true, that's this term here, and this is true. That's this term here. If I can find such a delta, that guarantees both of these, then their product is less than a times epsilon over a, which is, of course, epsilon. Now remember, my only control is delta, and the fact that x minus 2 is bounded above by delta in absolute value. Now, we need delta to be less than epsilon over a to satisfy this second condition. Now, to satisfy the first, to satisfy this condition, note that if x minus 2 is less than delta, then I can sandwich x minus 2 without an absolute value between delta and negative delta. I can add 4 to every term here, and I get negative delta plus 4 is less than x minus 2 plus 4, which is x plus 2, which is less than delta plus 4. And of course, if 4 were negative, then I would have something even less. So x plus 2 is sandwiched between delta plus 4 and negative delta plus 4. Therefore, x plus 2 is less than delta plus 4, which I'm going to call a, right? Because remember, I'm going to bound x plus 2 by a, right? That's the plan. Of course, I see that since a is equal to a positive number delta plus 4, a has to be greater than 4. Any number greater than 4. I'm free to choose any number. And yesterday, the Astros opened up the American League pennant race by beating the Cleveland Indians and scoring 7 runs in doing so. 7's greater than 4. I'll pick a equals 7. Now, I could have picked a equals 5. I could have picked a equals 4.1. I could have picked a equals 107. I chose 7. And I can pick any positive number greater than 4. So, if x minus 2 is less than delta, and delta is both less than epsilon over 7 and less than 3, right, 7 minus 4, then I get, if this is true, both of these statements are true. And if both of those statements are true, when I take their product, I get something bounded above by epsilon, which was my goal. So that's how I picked my delta, right? I start with my goal and say, how do I choose delta to force this to happen? And I work backwards until I can tease out this x minus 2 from this evaluation here. Now let's look at another example. Let's let D be the domain, and let D equal the set 1 over n, where n is every natural number, 1, 2, 3, and so on. Now, we know already that D has one accumulation point, x0 equals 0. So, if we're going to evaluate a limit of f, we can only consider the limit of f as x approaches 0. So our task is to show that the limit as x approaches 0 of f of x is 2, where f of x is x plus 2 divided by x plus 1. Well, let epsilon be a positive arbitrary number. Let delta be epsilon. If x is in the domain, then x equals 1 over k for some natural number k, because that's the definition of the domain. And x minus 0 for that x in the domain is equal to 1 over k, which is, of course, greater than 0 for every natural number. And I'm going to force to be less than delta, right? Because remember, I'm going to choose delta to bound x minus 0. And I chose delta specifically to be epsilon. Now let's evaluate f of x minus 2. The absolute value of f of x minus my proposed limit of 2 is, well, f of 1 over k minus 2 in absolute value. F of 1 over k is 1 over k plus 2 divided by 1 over k plus 1 minus 2. To simplify this fraction, let's multiply the numerator and denominator by k. I get that f of x is 1 plus 2k divided by 1 plus k. Let's express this 2 with a common denominator. Right. So since there's a common denominator, I can just add directly the numerator. 1 plus 2k minus 2 minus 2k. 2k minus 2k cancels. 1 minus 2 is negative 1. In absolute value, I get 1 divided by k plus 1. Now, of course, 1 divided by k plus 1 is less than 1 over k. 1 over k, by assumption, is less than delta, and delta is equal to epsilon. So I just proved that this is less than epsilon. And another epsilon bites the dust. We have developed a delta corresponding to epsilon that satisfies the limit condition. That's all for today.